This screencast has one central focus, and that is on colligative properties. As we go through these next 8 or 10 pages, there are 4 colligative properties which are talked about. The first one is vapor pressure, represented in just a few minutes by Raoult's law. Then we're going to talk about boiling point. Then we'll talk about freezing point. And then for the longest amount of time, we'll talk about osmotic pressure, because that relates an awful lot to biology. What you need to remember, and also be able to explain why, is when you add a solute to a solvent to create a solution, it makes the vapor pressure go down. It makes the boiling point of that solution go up. It makes the freezing point go down. We say it's depressed. And it can make the osmotic pressure increase or go up. So you're either elevating or depressing the values from what they would have been if you had a pure solvent with no solute added to it. So let's start with changes in vapor pressure. Raoult's law. And the idea here is if I have a beaker, I've drawn these before, and I got a lid on it and it's got some liquid in here. And if I start putting before I put any solute in there, I'm going to go back to blue. Some of that solvent is going to evaporate into the headspace above the liquid, and it'll be in equilibrium. You're going to have vapor going back into the liquid, and the liquid evaporating up into the vapor. You'll be at equilibrium. Now, if I add a solute to that, and I dump the solute in here, pictured in red, what's going to happen is that is going to interfere, especially with the solute particles that are located at the surface. That is going to interfere with the ability of the solvent to evaporate, and so you won't have quite as much solvent in the space and the line got erased there. You won't have quite as much solvent that will evaporate, and so your pressure is going to go down. The vapor pressure goes down because not as much solvent can evaporate because there are solute particles interfering with that process. So if we look at our 2 bullet points, the vapor pressure of the solvent is going to be lower because of the presence of the solute, and the vapor pressure of the solvent is going to be proportional to the amount of solute that we add. The more solute, the more it'll interfere with evaporation, and the more the vapor pressure is going to be reduced. And the proportionality, the way that we figure out what that new pressure is going to be, is by finding the mole fraction. The mole fraction, of course, is the fraction or the moles of solute divided by the moles of the solute plus the solvent. And we want to find the mole fraction of the solvent. And the mole fraction of the solvent would be divided by the mole fraction of the solute plus the solvent in the denominator. And the more solute you add, the smaller that fraction is going to be. That is what we mean by Raoult's law. So they give an example down here. If 95% of the molecules in a solution are solvent molecules, which means 5% of them are solute, then the vapor pressure of the solvent is going to be 95% of what it would have been without the solute. The pure solvent is 100%. Now notice it says it depends upon the number of particles. In this case, the particles are molecules. So if you go back up to the definition here, colligative properties are properties that depend upon the relative numbers of solute and solvent particles, which is why we often measure them in moles, as opposed to what those particles happen to be. Now, it's not that the identity of the particles makes no difference at all. At the very end of the chapter, we're going to realize that if your particles came from salts, ionic compounds, then you're going to have the Van 't Hoff factor, which is going to augment or increase the actual change, because ionic compounds split up in solvents like water. And if you have sodium chloride, for example, 10 particles of sodium chloride will become 20 particles of sodium and fluoride ions. And that would double the effect, just about, on these colligative properties. But again, we're going to get to that in the next screencast. So when we're doing Raoult's problems, the first thing we want to do is find the mole fraction. And in this case, we need to find our moles of water and our moles of ethylene glycol. And when we do that, the ethylene glycol is my solute, by the way, fancy name for antifreeze. And we put since we want to find the mole fraction of our solvent, water, that goes in the numerator. And the sum of both of them go in the denominator. And so we get a fraction of 0.888, or 88.8%. We're going to leave it as a fraction. And so the actual pressure of the solvent multiplied by the fraction, the mole fraction, reduces the pressure. Now, one of the reasons we use ethylene glycol, by the way, often is it easily dissolves in water. It is non-corrosive. And so things like metal and plastic and rubber tubing and so forth aren't going to be corroded. And it's relatively inexpensive. It's very easy to make. You also notice that ethylene glycol is not an ionic compound. It is, and therefore even it is polar, so it can dissolve in water, but we don't have to worry about the Van 't Hoff factor, as you'll see in the next screencast. And that's why another thing we often talk about with these solutes is that they are non-volatile. A non-volatile solute is going to be one that itself doesn't evaporate and contribute to the pressure that is in the headspace above the solvent. So that's why we talked about these non-volatile solutes. Ethylene glycol, antifreeze, doesn't evaporate very rapidly. We can also find the change in the pressure. And when we find the change in pressure, instead of using the mole fraction of the solvent, which is what we did earlier, we're going to do the mole fraction of the solute. And the negative sign is because we are depressing or lowering the pressure. We're finding how much the actual pressure is going to go down as a result of adding this solute at this amount to the solvent. All right, let's talk about boiling point elevation. In boiling point elevation, now we're going to add a solute to the solvent, and we're going to boil the water and see what happens. Now, the example that they start with is looking at benzene, which is a non-polar liquid, and says, suppose you have a solution of a non-volatile solute, one that doesn't evaporate easily, and we're putting that into the volatile solvent benzene. Benzene does evaporate, so all of the pressure above the solvent in the closed container will be due to the benzene. Now, if the non-volatile solute is in the quantity of about 0.2 moles per 100 grams of benzene, that gives us a mole fraction of benzene of 0.865. You can do the math. And therefore, we would multiply the ordinary vapor pressure of benzene at that particular temperature by the mole fraction of benzene in the solvent, because it's no longer a 1 or 100% because we've added a non-volatile solute, and that reduces my my vapor pressure of the benzene. Now, when we look at these vapor pressures here, you can see how much they're going to be depressed. If we pick a temperature, let's say of 60 degrees, and ordinarily we would have this vapor pressure of pure benzene in a container that's closed. Because we've added a solute, we've depressed it, and now it's down to, the pressure is now this much. Before it was this much, now it's down to this much at 60 degrees because of the addition of the solute. We can also look at the pressure, the temperature at which it would begin to boil. And the temperature at which it would begin to boil, if we look up here, normally it might boil at this temperature, at 80 degrees, the boiling point of benzene. But if we add the solute and we get to ordinary barometric normal pressure, 760 millimeters of mercury, now it's going to boil at this temperature, 5.1 degrees hotter. That is the boiling point elevation. It'll be 5.1 degrees higher than 80, or in other words, 85.1 degrees Celsius. And so the generic formula looks like this. Your change in boiling point, how much higher it's going to be, requires you to know the concentration of the solute in the solvent, the molality. And then this number here depends upon what is the solvent, the boiling point constant for the solvent. Is it benzene? Is it water? Is it some other liquid? And so you can see that the change in the boiling point temperature is proportional to the concentration. The greater the concentration of the solute in the solvent, the greater the delta T, the change in temperature, will be. And then in order to find the new boiling point temperature, you would take the old boiling point temperature and you would add the change in the boiling point to get the new, this is supposed to be a D, the new boiling point temperature. And looking at an example, it's pretty straightforward, but it is multiple steps. Sometimes, in this case, the first thing we need to do is to find out how many moles of our solute we have. In this case, the solute is eugenol. And then we're going to find the molality by dividing it by the kilograms of benzene, and that gives me my molality. And then once we know the molality, we can multiply by the constant from a chart, or it would be given to you on an AP test, to find your change. This is your change in your temperature. And then down here, you can take the original temperature and add the change to it to find the new boiling point of this solution. Couple things to keep in mind. Common mistakes. Make sure you keep track of which is the solute, which is the solvent. The solvent is, right there. Which is the solute, which is the solvent. The next thing you got to be really careful about is make sure that the solvent is in kilograms, because molality is defined as moles per kilogram, which of course means your solute has to be converted into moles as well. And then when you come down here to get the constant, sometimes if your solute can also be a solvent in other situations, you want to make sure you are getting the constant for the solvent that is used in this particular problem. Let's say that eugenol is a liquid. Well, some problem might have you dissolving something in eugenol, in which case you'd want the constant for eugenol. But in this case, benzene is the solvent, and we want to make sure that we get the constant for the solvent benzene. The last common mistake is if the question is asking, what is the final temp? What is the final temp? Every now and then somebody stops right there and they find the delta T, but not the final temp. And the classic example, of course, is antifreeze, which is also anaboyl, ethylene glycol. It's got those 2 carbons, and it's got the 2 hydroxyls off of each of those carbons. It elevates the boiling point, it depresses the freezing point. So here are some common solvents. Here are your boiling point constants, and here are your freezing point constants, because the freezing point problems are done the same way, except you'll notice that you subtract the change in temperature rather than add it to get your resulting temperature. And this picture over here is kind of interesting, that if you have some purple dye, which would be molecules with a large molar mass compared to water, it's dissolved in water, and then you begin to freeze it, the large molecules will want to stay in the liquid part, so as the ice forms around the outside, the large molecules will preferentially stay in the liquid state, and then you get the interesting, and also concentrate the dye, and so the dye no longer is evenly distributed throughout the solution, but it's concentrated in the middle part that hasn't really solidified, or will solidify eventually if it gets cold enough. All right, freezing point depression. In a freezing point depression, again, your change in freezing point is proportional to the concentration of the solute in the solvent. And the proportionality constant is this freezing point constant. Now, you can either use a positive value for K, in which case you need the negative sign in front of it, or what this book does, and it's pretty common, is to just make the freezing point constant negative to begin with. Because remember, you have to subtract this change in temperature from the original freezing point, because you depress or lower the freezing point. You don't elevate it like with the boiling point. So a solute interferes with the boiling process and makes it harder, requiring more energy, so the boiling point goes up. A solute also interferes with the freezing point, so it's got to be a lot colder before it will freeze and go into the crystalline solid state, and so the freezing point is depressed. And of course, with antifreeze, or with salt that you might put on the road or the sidewalk or your driveway in the wintertime, you want exactly that. You add the salts so that it's got to be a whole lot colder before ice will form and things will freeze on the road or the sidewalk. So if we look at one of these problems, it's done pretty much the same way. In this case, the first thing we want to do is we want to find our molality. Once we find our molality, because here we're using the formula, Recognize the formula that says that your delta T equals your freezing point constant times the molality. So you're using the formula. Once you have the molality, the molality, of course, is defined as moles per kilogram. So when you multiply by the mass of your solvent, in this case water, you can get your moles. And then once you know your moles, you can convert your moles into grams by knowing the molar mass of ethylene glycol. 3-step problem. And looking ahead, I'm just double checking on osmosis, and I think I'm going to save that to a later screencast.